Okay, it is now time to move on to section 3.3, which discusses differentiation rules. You all will be very happy to know that in section 3.3 we are learning tricks to find derivatives in a quicker way. We will no longer, after we learn all of this stuff, we will no longer have to always do f prime is equal to, because what we have done is f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x over h. As you have seen, that can sometimes take a lot of time and be a lot of work. So in section 3.3, we are going to learn a faster way to find these without having to do that. Okay, so I have several rules for us. The first one is the constant rule. And that is the derivative of a constant, so like the derivative of 2, the derivative of 8. This is a constant, okay? Whenever it's a constant, the derivative is always equal to 0. And let's think about why that might make sense, okay? Remember, what the derivative tells me is the slope at a point, right? That's the whole point, is I'm trying to find a slope. If this is a constant, then my y does not change, and therefore my slope is equal to 0. So that's why I get that. Another way to do that, if I was finding it the long way, it would be if I plugged in, quote, quote, if I plugged in x plus h, it's just a constant. So it's still just c minus f of x, also c over h. Well, look what happens there. That's the limit as h goes to 0 of 0 over h, which is 0. So that's why I get that. So as an example, the derivative of 2 would be equal to 0 because it's a constant. On that same note, the derivative of something like negative 4, so d dx of negative 4 would also be 0. Again, because it's a constant. So if I have a constant, the derivative is equal to 0. There's another really helpful rule. That rule is called the linear rule. And this says the derivative of x is equal to 1. The derivative of x is equal to 1. Let's think about why that might make sense. So I know I would do the limit as h goes to 0 of f of x plus h. So I would do x plus h minus f of x, so minus x over h. Well, x is going to cancel out with x, so that's the limit as h goes to 0 of h over h. Well, h over h is just a 1. So that's the limit as h goes to 0 of 1, which is 1. So the derivative of x is equal to 1. That's a helpful rule too. This next one is a very important one. We use it all the time. It's used a lot, and it's called the power rule. Put a star by this one. Remember this rule because it is used the most. We use this rule all the time. Again, it's called the power rule. And what this rule says is that the derivative of x to a power, so like I'll just say x to the n, so like x squared, x to the third, x to the ninth, all of that stuff. If it's x to a power, all I do is I'm going to bring my power down to the front, so it's going to be n times x to the power of 1 less of what it already was. So it was n, so now it's n minus 1. So the derivative of x to the n is equal to n times x to the power of n minus 1. Let's do some examples of that. Let's find the derivative of x squared. We did this the long way whenever we did section 3.1 and 3.2. Okay, we did this the long way, but now I'm going to use this rule. Okay, so here I have x to the 2, so my power is 2. So using this rule, all I do is bring my power down to the front, so that's going to be 2, and I'm going to multiply that by x to the power of 1 less of what it already was here. So it was 2, so now it's going to be to the first. But since it's just x to the first, I can just write that as 2x. The derivative of x squared is equal to 2x. Again, we did this the long way before now, but now we can do it using this rule here. Let's do another example. Let's do the derivative of x to the third. The derivative of x to the third. Again, I have x to a power, so I can just bring this power down to the front. So that's going to be 3. And then it's going to be x to the power of 1 less of what I already had. I already had a 3, so go down by 1, and that's 3x squared. So the derivative of x to the third is equal to 3x squared. Very nice, very easy, very quick. Another example, derivative of x to the 10th. Derivative of x to the 10th. Again, I have x to a power. So it was 10, so I bring my 10 down to the front. X to the power of, I'm going to decrease that by 1, so now it's a 9. 10x to the 9th. So like I said, this is a very helpful rule, because if I had done this the long way, I would have had to have done x plus h to the 10th, which would have been humongous, right? All just to break it down and get this, right? So doing the power rule saves us a lot of time. Again, just bring my power down to the front, decrease my power by 1. So 10 from the 10, x to the 9th. Let's do some more examples. We can actually use this to find derivatives that don't look like you could use the power rule, but you actually can. So for an example, let's do the derivative of 1 over x squared. Now this doesn't look like we could use the power rule because it's 1 over stuff, right? But remember, whenever I have 1 over x to some stuff, I can rewrite this as the derivative of x to the negative 2, right? A power in the denominator means I can write it as negative. So this is like saying x to the negative 2. Now that I have it in the form of x to a power, I can do the power rule. So again, just like we have done, bring our power down, so negative 2. And then I'm going to multiply that by x to the power of 1 less of what it already was. Negative 2 minus 1 is equal to negative 3. Negative 3. So I could stop right there, and that's fine. It doesn't matter. Or you can simply this by making it, since the power is negative, I can bring it down. So negative 2 over x to the third. But like I said, you can just stop right here, and that's okay. It doesn't matter. This is what I want to know. I want to make sure you can apply the power rule. So as long as you can get here, I'm good with it. Let's do another example kind of like that one. Let's do the derivative of 1 over x to the 9th. It's kind of hard to read. Let me rewrite that. 1 over x to the 9th. Again, this doesn't look like I can use the power rule, but since it's 1 over that, I can rewrite it as x to the negative 9th. Now, since I rewrote it like that, just like I did up here, I can bring my power down, negative 9, x to the power of, I can decrease my power by a 1. Negative 9 minus 1 is negative 10. So you can either stop right there or rewrite it as negative 9 over x to the 10th. Either way, it doesn't matter. Another example where it doesn't look like we can use the power rule, but we actually can, is when we do the derivative of something like the square root of x. Derivative of the square root of x. This is another one we actually did in section 3.2. we did this one. So again, it doesn't look like I can use the power rule right now, but remember, having a square root is like having a power of 1 over 2. So I can rewrite the square root of x to be x to the power of 1/2. That's the same thing as the square root. Same thing. So now it is x to a power, so I can use the power rule. Remember the power rule? Bring my power down to the front, so that's 1/2 times x to the power of 1 less of 1/2. So I've got to do 1/2 minus 1. It's like saying 1/2 minus 2 over 2. 1 minus 2 is negative 1. So the power is now negative 1 over 2. I could stop right there, and that's okay. But remember, negative 1 over 2 means I can bring it to the denominator. So 1 over 2, x to the 1/2. And x to the 1/2 is like saying the square root of x. So I could write that as 1 over 2 square roots of x. Again, that's exactly what we got whenever we did this in 3.2. But now it saved us a lot of time without having to actually like multiply by the conjugate and doing all of that stuff we had to do originally, right? I can do it like this now. So the power rule is a very helpful tool. We use it a lot in this class. And actually all math. From here on out, any math class you take, the power rule is going to help you a ton. So now that we have a few rules, I want to add some rules that are going to help us use several of these tricks at one time. Okay, so that's what we're going to do now. The first one says that if you're taking the derivative of one function plus another one, then what I can actually do is I can split this up and do the derivative of each one of these things. So instead of having to add them and then do all that, I can just take the derivative of each term. So that's going to be the derivative of f of x plus the derivative of g of x. I can just do each term. Same thing if I am subtracting them. So f of x minus g of x. I can just do each one and then subtract them. So that's going to help us out. It also works where if I'm multiplying by a constant, so if I'm saying a constant times f of x, I can just bring my constant out to the front and multiply it by the derivative of f of x. So let's do some examples of using these rules here. So example. Let's find the derivative of 2x. The derivative of 2x. So notice here what this is this is the constant 2 times an x. Well, we already know how to take the derivative of just an x, right? So what I can actually do is bring this constant out to the front, 2 times the derivative of x. And since I know this, I can just take the derivative of the x. Remember we said the derivative of x is a 1. So that's 2 times 1, which is 2. Again, that's using this rule right here, the third one, where if I'm multiplying by a constant, I can just bring the constant out to the front. So on that note, let's see what happens when it's 3x. So the derivative of 3x. I would do the same thing, right? I have 3 times x, so I can just bring my 3 out front. 3 times the derivative of x, and as we have said, the derivative of the x is just a 1. So that's just 3 times 1, which equals 3. So if you're noticing a pattern here, the derivative of a constant times an x is just the constant. So if I was doing the derivative of 25x, that would just be 25. So that's a helpful little rule too. That'll help us out a lot. Let's do some more examples using these first two rules up here. I want to practice using those rules. Well, actually, sorry. Before we do that, I do have a few more using that constant rule. Let's find the derivative of 3x squared. 3x squared. So again, I know how to work with x squared. So I have 3 times that. So I can just bring my 3 out to the front. Now I know how to find this because it's x to a power, right? It's x squared. So I can bring my 2 down. I have 3 from this 3. I can bring my 2 down, and that'll make it x to the first. So I don't need to actually put the 1 right there. 3 times 2x is 6x. So as you can see, what I can actually do is when I bring my power down, I can just do that power times what's out front right here, right? So I could have just done 2 times 3, which is a 6, and then x to the power of a 1. So x to the first. Using that same thought process, let's find the derivative of negative 2x to the 6th. Negative 2x to the 6th. So since this is x to a power, I can do the power rule. So I can bring my power down, which would make it 6 times negative 2. Multiply those and you get negative 12 times x to the power of. Remember, it's 1 less. 6 minus 1 is 5. So negative 12x to the 5th. Again, when I bring my power down to the front, I can just do that power times what's right here. So negative 12x to the 5th. Another example of that, just to make sure we're clear. The derivative of 7x to the 10th. Again, I bring my 10 down. 10 times 7 is 70 times x to the power of. It was 10 minus 1 and you get 9. So that's a way I can use the power rule. The most common way we're going to use the power rule is when we do stuff like this. The derivative of 4x squared minus 3x plus 2. Derivative of something like that. So again, so far what we would have done was we would have had to plug in x plus h, work everything out, and then minus f of x, divide it by h, and all of that stuff, right? That's what we have done. Well, now with the power rule, I can do this a much quicker way. Remember I said if I'm adding or subtracting a bunch of terms, I can just do term by term. Okay? So I'm going to start with the derivative of 4x squared. Okay? We're going to start with the derivative of 4x squared. Since I have x to a power, I can just bring my power down to the front. 2 times 4 is equal to 8. Right? 2 times 4 is 8. I'm going to multiply that by x raised to the power of 1 less of what this power already was. So it was 2. 2 minus 1 is 1. So this is 8x to the first. But again, I don't have to actually put the 1 right there. So for 4x squared, I got 8x. Now I move on to the next term. Minus the derivative of 3x. Well, we said whenever I have a constant times the x, it's just whatever the constant is, right? We said that over here. We did that right here. Right? So using that idea, the derivative of 3x is 3. So minus 3. Then I move on to the last term, which is 2, which is a constant. We said the derivative of a constant is always 0. So I don't even need it, and I can just stop right there. Because the derivative of a constant is equal to 0. So I can just leave it out. That's really helpful. Let's do another one. Isn't this way quicker, though? Let's do the derivative of, let's do a long one. 9x to the 5th minus 4x to the 4th plus 10x to the 3rd plus 3x squared minus 4x plus 982. So this looks really hard, and if I did this the long way, it would take forever, because I would have x plus h to the 5th, x plus h to the 4th, x plus h to the 3rd, x plus h squared, x plus h. All of that, have to work it out, cross out terms, and it would take a really long time. Using this power rule and every other rule, this actually doesn't take long at all, and we can do this very quickly. So remember, I can bring my power down to the front. So 5 times 9 is 45 times x. My power was 5 minus 1, and we get to the 4th. Move on to my next term. Bring down my power. 4 times negative 4 is negative 16. X to the power of minus 1 right here. 4 minus 1 is 3. Do it again. Bring my power down to the front. 3 times 10 is positive 30. Bring my power down by a 1. 3 minus 1 is 2. Move on to the next term. It was 3x squared. Bring my 2 down. 2 times 3 is 6, which would make it x to the first, so just an x. The derivative of negative 4x, as we have seen, I can just use the negative 4. And then the derivative of 982, since this is a constant, it's equal to 0. So I can stop right there. So like I said, it's taking problems that would have been really hard if I had to like do the whole f of x plus h minus f of x thing. Now it isn't bad. We did that very quickly, right? Just bring the power down and decrease it by a 1. So let's use these new tricks and apply it to finding the equation of a tangent line. So example. Find the equation of the line tangent to the function f of x equals x squared minus 4x plus 6 at x equal to 1. So we did these. We've actually done these. We did it in section 3.1 and 3.2. How I start this is I need a point and I need our slope, right? I can get a point by plugging in a 1. So f of 1 equals 1 squared minus 4 times 1 plus 6. 1 squared is 1. 4 times 1 is 4 plus 6. 1 minus 4 is equal to negative 3. Negative 3 plus 6 is 3. So the point that I know is 1, 3. So that's helpful. I know a point. But I also need a slope. Remember we said a slope of a tangent line is the derivative at that point. So I need to find the derivative of this guy. Now, like I said, so far we have had to do the whole f of x plus h minus f of x over h. But now with these new rules, I don't have to. Now I can just use the power rule to find what f prime of x is. So for x squared, again, we can just bring my 2 down to the front, which makes it 2. And now I have x to the first because I do 2 minus a 1. So 2x. For the negative 4x part, I could just leave the negative 4 because we said whenever it's a constant times the x, I just use the constant. And then the derivative of 6 is 0, so I can just leave that off. So this took a lot less time than doing it the long way, right? So now I have f prime of x. I'm doing this at x equals to 1, so our slope is f prime at 1. So just plug in a 1. 2 times 1 minus 4. 2 times 1 is 2. 2 minus 4 is negative 2. So now I have my point and I have my slope. So I'm going to put this into point slope form. Remember we reviewed this in section 3.1. Point slope form is y minus the y that I know, which is 3, equals our slope, which we just said is negative 2, times x minus the x, which is 1. Now I just solve this for the y. Distribute the negative 2. Y minus 3 equals negative 2x plus 2, and then add 3. So y equals negative 2x plus 5. So my point of showing you guys this one is to show that these tricks really help me save time, right? Because how I've done it before is when I found what the slope was, I would have had to have done the limit as h goes to 0 of f of 1 plus h minus f of 1 over h, which could have been a lot of work. So instead of doing all of that, I just find f prime of x using the power rule and then plug in a 1. We do have some more rules. two more I want to do right now. This first one is called the power rule. Or sorry, we already did that. Product rule. The product rule, I'm going to use that whenever I'm finding the derivative of a product. So f of x times g of x. Times right there. Now, it would be extremely nice if it was as clear as just doing the derivative of each part and saying this times that, right? That would be very nice. However, it doesn't work like that. When you are doing the derivative of a product, this is how it's done. Take the derivative of the first part, so f prime of x, and multiply that by this part. So do the derivative of the first part, leave the second part. Plus, then switch them. Leave this first part, so f of x, times the derivative of that part, g prime of x. Again, I do this when I'm doing the derivative of a product. Okay, of a product. Do the first part, leave that part, leave that part, do the derivative of the second part. So let's do some examples of that. Let's do the derivative of 2x to the fifth times the quantity 4x squared plus x. 2x to the fifth times 4x squared plus x. Now, something I could do is just distribute that through here and then do the power rule. That's fine, but I wanted to show you this using the product rule. Okay, so using the product rule, again, what the rule says is we're going to find the derivative of the first part. In this case, my first part is 2x to the fifth. Okay, so I'm going to find the derivative of 2x to the fifth. I do that by bringing down my 5. 5 times 2 is 10, times x to the power of 1 less of that is 4. So I did the derivative of the first part. Now I'm going to multiply that by leaving the second part alone. Just leave it. Now I'm going to do plus. Now I'm going to leave the first part, which was 2x to the fifth, and I'm going to multiply that by the derivative of the second part. So the derivative of 4x squared plus x, for the 4x squared part, I bring my 2 down, which makes it 8. So 8x to the first, because I go down by a 1. 2 minus 1 is 1. And then plus the derivative of x is 1. So to recap, what I did was the derivative of the first part, leave that part. That's how I got this. And then plus, leave the first part, do that part. So 2x to the fifth, which I left, times the derivative of 4x squared plus x. Now, something I want to make clear is you can just leave it like this. I'm not as concerned about you knowing how to simplify stuff. I just want to make sure you know the calculus concepts, right? And so leaving it right here is completely fine. Just leave it there. But of course, if you wanted to, you could distribute this guy through here, distribute over there, find like terms and all of that stuff. But you don't have to. Just leave it here and that's fine. Let's do another example using the power rule. Product rule. These P words are going to trip me up. This example, we're going to find the derivative of x squared plus 2 times 3x cubed minus 5x. Technically, I should have put a bracket around here to make it clear I want to do the derivative of the whole thing. My fault. I should have put that there. Like that. So just like we did on the last one, we are going to use the product rule because this is a product. Okay? So that's going to be equal to the derivative of the first part, the derivative of x squared plus 2. From the x squared part, I get 2x. From the 2, I get 0, so I can just leave that as 2x. Times, leave the second part, so we're just going to leave 3x cubed minus 5x. Then I'm going to add, now I'm going to leave the first part, so x squared plus 2 is going to just stay. and then find the derivative of this part. So the derivative of 3x to the third, bring my 3 down. 3 times 3 is 9. X to the power of 3 minus 1 is 2. Then the derivative of negative 5x is negative 5. There it is. That is the derivative of that. We're going to do a few more examples, a few more examples of the product rule. Product rule, I just want to make sure I said that. Product rule, just in case I messed up again. We're going to find the derivative of 3x to the fourth minus 2x squared plus 3x times 9x to the third minus 4x squared plus 3x minus 2. So this one has more terms, it's longer and all of that stuff, but the process is the same, so don't let something like this scare you, okay? Because I'm doing it the same way. Even though there are more terms, it's still doing the same thing. So remember we said we do the derivative of the first part, the derivative of 3x to the fourth, bring my 4 down, 4 times 3 is 12, x to the power of 4 minus 1, which is 3. Bring my 2 down over here, that gives me negative 4x to the first, and then the derivative of 3x is just 3. So I did the derivative of the first part. Now I'm going to leave the second part. Don't do anything with that. And then I'm going to do plus, now switch them. So now I'm going to leave the first part. So leave 3x to the fourth minus 2x squared plus 3x. I'm going to multiply that by the derivative of this part. For 9x to the third, bring my 3 down. 3 times 9 is 27. And then now that's x squared because I bring it down by a 1. For negative 4x squared, bring 2 down, and that makes it negative 8x. See if I can make this fit. And then from the 3x, again, that's just 3. The derivative of negative 2 is equal to 0, so I don't even have to put that. Oh, that's supposed to be a parentheses. I don't know what just happened. 3 parentheses. There we go. So again, it looks harder because there are more terms there, but it still isn't bad. And like I said, you can just leave it like this. No use in trying to simplify that. One more using the product rule. This one, there's a reason I wanted to do it, and you will see why whenever I write it down. Let's find the derivative of 2x cubed times 4x squared plus 3x minus 2 times 8x squared plus 9x plus 4. Now the reason I wanted to do this one is because I have 3 things here that I'm multiplying, right? There's 3 of them. The product rule only works if there are only 2, right? A thing times a thing. Only if there are 2. It does not work if there are 3 of them. So there are many ways I can do this. The first thing is I can actually distribute 2x to the third to one of these. It doesn't matter which one. To one of them. In which case I would only have 2 things. And then I could use the product rule from that. So I could do that. Distribute this guy. And then I would only have 2 terms. And so then I can do it. Another way, and the way I'm going to show you guys, is I can actually use the product rule twice. Okay, I can use the product rule to find the derivative of the first part, which is going to help me when I do the product rule for the whole thing. Okay, so the product rule for the whole thing tells me I'm going to first find the derivative of the first part. So I'm splitting this into one term. I'm saying this is one term. This one times that one, right? So first thing, I find the derivative of this. Well, to find the derivative of this, I have to use the product rule. So I'm going to use the product rule here. Product rule says derivative of the first. Bring my 3 down. 3 times 2 is 6. That makes it x squared. Leave that part. plus, leave the first part, 2x cubed, derivative of this part. Derivative of 4x squared, I bring my 2 down. 2 times 4 is 8, so 8x. Derivative of 3x is 3. So there we go. That is the derivative of all of this stuff. Now, I need to multiply that by leaving this part. So leave 8x squared plus 9x plus 4. Now I have to do plus, leave the first part, so leave 2x cubed times 4x squared plus 3x minus 2, times the derivative of this part right here. For 8x squared, we bring our 2 down. 2 times 8 is 16, so 16x. Derivative of 9x is 9. I wouldn't have made that fit right here, and so that's why I brought it down, but this should be all on one line. I just didn't have space, but that's how we do that one. So again, when there are three, there are a lot of ways to do that, but what I do is just group the first two and make that one term. So with the product rule, whenever I say take the derivative of the first part, that means all of this. Well, when I do that, I've got to use the product rule, which is what I did. So the derivative of the first times the second plus the first times the derivative of the second. Same thing, just with more terms. Okay, so just like we have a product rule, you can probably expect we have a quotient rule. We have a quotient rule as well. So let's look at the quotient rule. The quotient rule says that if you're finding the derivative of a function divided by a function, so if you are dividing, then the derivative of that is going to be the following. The bottom times the derivative of the top minus the top times the derivative of the bottom. All of that divided by the original denominator squared. So some people have a hard time remembering this because it's a lot, right? So a trick people have done is low d high minus high d low. And what that means is the bottom times the derivative of the top minus the top times the derivative of the bottom. So low d high minus high d low. I've heard that. All over low squared. So let's do some examples of using the quotient rule. Let's find the derivative of 5x squared over 4x plus 3. So again, I know I'm going to use the quotient rule because this is a quotient. Okay. So using the quotient rule, we start with low d high, so the denominator times the derivative of the numerator. Bring my 2 down. 2 times 5 is 10, so that makes it 10x, minus high d low. So leave the numerator times the derivative of the denominator. The derivative of 4x is just 4. The derivative of 3 is 0. So we just have 4. All of that over the denominator, which is 4x plus 3, squared. Again, you don't have to simplify this. You can just stop right there and you're good. So again, low d high minus high d low over low squared. Another example of using the quotient rule. Let's find the derivative of 3x plus 1 over 4x minus 3. So again, I know I'm going to use the quotient rule because it's a quotient. So we start with low d high, so leave the denominator, times the derivative of the numerator. The derivative of 3x is 3. The derivative of 1 is 0. Minus high d low. So leave the numerator times the derivative of the denominator. So the derivative of 4x is 4. The derivative of negative 3 is 0. All of that over the denominator, which is 4x minus 3 squared. And there it is. Again, as y'all can probably tell, this is a lot quicker than doing it using the whole f of x plus h minus f of x over h thing. I have just 2 more examples I want to do. So example, let's find the derivative of 4x to the third minus 3x squared plus 9x to the negative 2 over 2x to the third plus 9x squared minus 2x plus 1. I'm realizing now the power should not have been a negative 2. It should have said 9x minus 2. So sorry about that. I was like, that's really weird. I don't know why I would have put that. Anyway, 9x minus 2. Okay, again, I know I'm going to use the quotient rule because this is a quotient. So let's write it out. Remember, we start with low d high. So leave the denominator. And then we're going to multiply that by the derivative of the top part. For 4x to the third, we bring our 3 down. 3 times 4 is 12. And now that's x squared, because I do 3 minus 1. Bring down my 2. 2 times the negative 3 is negative 6. And that's just an x, because 2 minus 1 is 1. Derivative of 9x is just 9. Derivative of negative 2 is 0. Subtract high d low. So now leave the numerator. I thought I left myself enough room. Leave the numerator. Find the derivative of the denominator. So 2x to the third, bring my 3 down. That becomes 6x squared. Plus 9x squared, so bring my 2 down. That makes it 18. So 18x. So sorry. The negative 2x becomes negative 2. Negative 2. Parentheses. I'm so sorry about that. All of that over the denominator squared. So 2x to the third plus 9x squared minus 2x plus 1 squared. And there it is. Again, don't try to simplify that. That's just going to be a mess. We're good with that. So again, this should say 6x squared plus 18x minus 2. Sorry about that. I ran out of room. I should have scooted that over a little bit. One more example. This is a good example. This is applying this stuff to something we are going to do in chapter 4, I think it is. But we can actually do it now, so we're doing a preview. Determine the values of x for which the function f of x equals x cubed minus 7x squared plus 8x plus 1 has a horizontal tangent. So let's think about that. A horizontal tangent means that the tangent line at that point is going to be horizontal, right? Where a horizontal line has a slope equal to 0. Horizontal tangent means I'm looking for where my slope is equal to 0. That's the whole point. Well, what we have learned so far is that the slope, I can find that by finding the derivative, right? So what this is really wanting to know is where is the derivative of x equal to 0. That's the whole thing. That's what I want to do. So let's find what the derivative is, f prime of x. Bring my 3 down, and that makes it 3x squared, because I'm minus 1. Bring my 2 down, which makes it negative 14x to the first, so don't have to have it there. Derivative of 8x is just 8. And then the derivative of 1 is equal to 0, so I don't have to put that there. Well, I want to know where this is equal to 0. So set it equal to 0, and let's solve that. So I would try to factor out 3x squared minus 14x plus 8. If you were to factor that, you would get 3x minus 2 times x minus 4. I believe we reviewed factoring somewhere in chapter 1. So if you want to go back and rewatch all of that stuff, we reviewed how to find this. Now that we've factored it out, set both factors equal to 0 and solve them for x. So I would add 2, divide by 3, so x is equal to 2/3. So what happens at 2/3? Add 4 for this one, you get x equal to 4. So there are horizontal tangent lines at x equals to 2/3 and x equals to 4. All right, that is all I have for y'all. So moving on, we are going to actually apply this stuff to application problems. That's our next step. So good luck. I will see y'all then.